Another application of what you've already learned in terms of forces and energy and momentum comes in oscillating systems, which you're already really familiar with. We see them most often when we look at, say, a spring system that can oscillate. So you put a mass on a spring and it oscillates up and down and around the equilibrium position. And we talk about this in terms of simple harmonic oscillation. And what we mean by that is something that something that oscillates back and forth that we can describe as a sine or a cosine wave. And it turns out that a spring is a system that we can do that. We can describe, in this case, its vertical motion, y as a function of t, for example, as a sine wave that goes like this. And its amplitude, its peak, would be sort of how far we pulled it to start. And that would be this distance is a, is given as its amplitude. And then it has a period. And the period of motion is when it starts to repeat itself. So when it goes from here, goes through a full cycle and then comes back. So that would be one period of motion, which we write with a capital T because it's in seconds, it's time. So this capital T is called the period of the motion, and it's measured in seconds. And A is called the amplitude. And in this case, that would be measured in meters, right? Because it's a position. And we can describe the motion as y is equal to A sine of, at least this motion, 2 pi over the period times t. Because if we notice that this works, when t equals 0, we get 0. When t equals the period, then we get 2 pi, which would be what's happening right here. And so that describes this. So very often you'll see this written as y is equal to A sine of omega t. Yes, the omega that we saw in rotational motion. We'll get back to that. But this is in radians per second because it's got to end up in radians when we get finished. So this is radians per second, or like 2 pi is radians per second. So omega is 2 pi over the period, and it has units of radians per second, just like it did before, even though there's nothing rotating here. It's just because the units are the same that we use the same expression. And then there's one other term that we use here. Sometimes we use the inverse of the period, and that is the frequency. So the frequency is 1 over the period, and that is measured in 1 over seconds, which is in hertz. So that's another notation that we use to describe that. So simple harmonic motion can be described as a sine wave. It could also be described by a cosine wave. So we could have something where it started a little differently, and it starts like this, but it has the same period, and then we would say y of t is equal to a cosine of omega t. So we can often, you'll see this written more generally as y as a function of t is equal to a cosine omega t plus some phase angle. So you'll see that where you can adjust that by 90 degrees or pi over 2, because a cosine, this is y of t versus t, a cosine and a sine are the same, they're just shifted by 90 degrees, okay, or pi over 2. So you'll see this as a description of our simple harmonic oscillation. So our next step is to see what kinds of systems fall under this case and talk about how it is that this describes the motion of a spring. I hope you're not surprised by that because of the bouncing up and down, and this gives us a way in also to start to understand waves. So this looks sort of like a wave-like motion as well. So this is sort of fundamental to all of that.